Bismillahirrahmanirrahim. Assalamu alaikum. Lecture 4 of the discrete structures, CSC 102. In the previous lecture we have studied conditional propositions, their negation, inverse and converse, contraposition of conditional statements, biconditionals, and necessary and sufficient conditions of conditional statements. We have studied also the logical equivalence of conditional statements also. In today's lecture, I shall give you some applications of logic in computer science. Today's lecture outline is this. First of all, I shall explain you some basic logic gates, and then we shall construct circuits by using logic gates, and then we shall study some Boolean algebra which will help us to construct circuits of addition in the computer. And also we shall see the logical equivalence of circuits at the end. So first, what are the basic logic gates? The first logic gate is NOT. As the logical connective, we have the logical connective NOT. We have a basic logic gate which is called NOT, which is said to be NOT, and its form is, or it is written as this, as you have seen on the screen. This is the form of the NOT logic gate. It has input variable or input proposition as x. So as you know that NOT operator is, or NOT logical connective is applied to only one proposition. So x is here input, and the output is represented by x bar or x tilde x or not x, as I have told you. We can see it also as not x. So if the input of this not logic gate is x, then its output is x bar or not x, or you can say, you can write it as not x. So another basic logic gate is AND, which is also the conjunction operator between two propositions. So as we know that conjunction operator has two, conjunction operator is basically applied between two propositions. As we have seen in previous lectures that we take, if we have two propositions P and Q, then conjunction operator is P and Q. So here we have a basic logic gate which is called AND, and it can be represented or expressed by this symbol. This is the symbol. It has two inputs, x and y, or you can say P or Q, and the AND logic gate form is like this. Its output is xy. We can write xy, or we can write x and y. This is basically equivalent to xy. It's basically abbreviated form of x and y. So the next logical operator, logic gate, is OR. This we have studied that OR is basically disjunction operator. It is applied to two propositions P or Q. And in logic gates, or in logic gates, we express it as x plus y, or this is basically logically equivalent to x or y. These are just the different notations which we use in logic gates. Its form is like this. The logic gate the OR logic gate is basically of this form. This is the form of OR logic gate. It has two inputs X and Y, and it has one output X plus Y. Basically this logic gate operates same as the disjunction operator. Same is the case for the AND operator, as if we have two possible basically values of X. If X is true and Y is true, then the output of this logic gate will be true. If X is true, Y is false, then AND operator, as by disjunction, the output will be false. Basically all these logic gates can be expressed using truth tables also, as we have constructed the truth table of negation, not, conjunction and disjunction. These logic gates have same possible values and outputs as we have constructed the truth tables of these logical connectives or operators. For example, if we have OR operator, example, this logic gate, it has two inputs X and Y, and this is basically, its form is like this. It is constructed as you have seen in previous slide. This is basically the form of OR logic gate. X and Y are two inputs, and its output is X plus Y, or we can write X or Y, which is here, it is disjunction. Now the truth table here is the same. The possibilities of this logic gate is same as the truth table of the disjunction operator. Here usually the truth values in logic gates are denoted by 1 and 0. 1 stands for true and 0 stands for false. So if we write X as true, then it is 1, X true, X false, and Y, if Y is true, Y is false, Y is true, Y is false. As we have seen in your previous lectures that for two propositions we have 4 possibilities. Now the output of this logic gate OR is 1 if both inputs are 1, X and Y. If both X and Y are 1, then the output is 1. If X is 1 but Y is 0, then the output is 1. If X is 0 and Y is 1, then output is 1. And if both inputs are 0, then output is 0. So this logic gate basically, it behaves same as the disjunction operator X or Y. It is false when both X and Y are false, otherwise it is true. Similarly, we can construct truth tables or all possible values of these logic gates in the same way. There are other basic logic gates. For example, the third logic gate, which is called NAND, and it is represented, basically NAND is abbreviation of not AND. Not AND, if we have not AND operator, then it is basically read as NAND, N-A-N-D. And this operator basically is the negation of X and Y. So this is called NAND operator, and its representation is symbolic representation is basically same as AND operator, but the difference is that we construct a circle here which shows that this is a NAND operator or NAND basic logic gate. Its truth table we can also construct it. It has basically two inputs X and Y, and the output is basically x y bar. What does it mean? It means not x and y. We can say it here also, not x and y, but it is abbreviated as xy bar. As I have told you, the negation symbol not x is represented by x bar or tilde x, as we have written it here. The next operator or next basic logic gate is NOR. This is basically not OR. This is the abbreviation of not OR, and this logic gate basically is applied to the negation of P disjunction Q. Means P or Q and the negation of whole this compound proposition. And this logic gate is abbreviated as NOR, and its symbolic representation is just like OR logic gate, but the difference is that at the tip here we draw a circle. It also has two inputs, x and y, and the output is basically not x plus y, or we can write not x or y. So in logic gates, the representation of the symbolic representation of disjunction and conjunction are slightly different, but we can represent them even in this way, not x and y and not x or y. The next logic gate is basically XOR. XOR, you know, XOR logic gate is basically the form of OR operator in which the exactly one of x or y is true. We have studied XOR operator in the first lecture. So the symbolic representation of XOR logic gate is like OR logic gate, but we draw a line here before the OR logic gate here in this case. So this is basically the symbolic representation of XOR basic logic gate. So it's written as x plus circle, as we write the XOR operator. You know, we write it in the previous lecture as P plus circle Q. It has also two inputs, and the output is x plus basically XOR of x XOR y. Now we can construct circuits for a given compound propositions. For example, if we are given a compound proposition P or Q and not P, for example, not Q, for example. So this is a basically compound proposition. We can construct a circuit by using logic gates which corresponds this compound proposition, or sometimes we say it Boolean expression. I shall explain you the Boolean expressions later on when we shall see, or we shall study some examples or applications of logic gates in computer. So we have two propositions here. First of all, we have to decide how many propositions we have. We have two propositions here, P and Q. So we write them P and Q as, and we draw two lines here corresponding to P and Q. Now you must know the order of preference of logical operators or logical connectives. I repeat here, the first preference is given to the NOT operator, and then AND, conjunction or disjunction operators. The second preference is this, and then we give the preference to the implication, conditional statement, and then biconditional statement. So this is the order of preference of logical connectives. Unless there are brackets, parentheses given in the logical expression. For example, if we have here P or Q bracket, so we must give preference to P or Q, and then AND. Here we have OR operator, AND operator, NOT operator. So the first preference is given to NOT Q, then AND, and then P or Q. If here we have bracket, we can basically decide the preference of logical connectives in the logical expression. So we have two basically propositions here, P and Q. So to construct a circuit, how we shall proceed? P, Q, we shall draw lines here. Now there is a P or Q here, so we know the OR basic logic gate. We construct here a OR basic logic gate like this. Basically OR logic gate has this form, this. So this basically represents P or Q. Here we can write P or Q, this, or we can write P plus Q as we have seen the notation in the previous slide. Now another we have NOT Q. So the NOT Q preference is given to the NOT Q, and then we draw another line from here, and we draw a NOT operator here, which is this. Basically the form of the NOT operator is this, whose output is basically, here we draw a little circle also. Now we have two expressions here basically which are connected by AND operator. Here we have this expression, and here we have P or Q. Two expressions are connected by AND operator. So here we have connected the first expression P or Q, and the next we have constructed Q. Basically Q is coming right here also, and Q is going to this logic gate also. Basically Q is the input of this logic gate also, and Q is the input of this logic gate also. Basically this represents this expression, and the other represents this expression. Now these two expressions are connected by the conjunction operator AND. How we connect them? We can draw a line here, and we can proceed it here, and now there is a AND operator between these two expressions. We draw a AND logic gate here, this, and we have output here. Now here we have a P or Q, here we have a NOT Q, and these two connected by the conjunction operator, this again AND operator, and here we get from here we have P or Q, and this is connected basically by AND operator. This is AND operator. We can write it A and AND operator here, and we can write it here OR operator, and here we can write NOT operator basically. So here we have P or Q and NOT Q, this. So for this expression, for this compound proposition or logical expression, we can construct a circuit like this. So this circuit represents the given this expression. So, or we can say that corresponding to this expression, we can draw a circuit using logic gates like this. So this is basically the output. This is called the output of a circle, which is usually denoted by S. So we can give inputs here to this circuit, and we can find the output of this circuit. For example, if we give P as a true value, which is 1, and Q as a false value, which is 0. Now these are the particular truth values of P and Q. So the inputs for P is 1 and input for Q is 0. So now we see that if we give the input to this circuit as 1, 0, what will be the output? So here we have OR. P is 1, Q is 0. OR operator will give us here what? 1, because 1 is true and 1 is false. Q is 0, and not Q will be 1. Not Q will give us 1 output. Now here we have 1 and we have 1 here, and we have AND operator here. So what will be the output here? This will be 1, because we have 1 here and we have 1 here. And in the conjunction operator, the AND operator, if both inputs or both P and Q are 1, 1, then the P and Q is what? As 1. So if we give particular inputs to a circuit, we can find an output. And we can also see that for any logical expression or compound proposition, we can construct a circuit, and by giving inputs to the input variables, we can find the output. I take another example here. In this, we shall construct a circuit for the expression given by P and Q, or not P and Q, or P and not Q. So in this expression we have actually 3 sub expressions, you can say. P and Q is enclosed by brackets, not P and Q, and P and not Q. These 3 expressions are connected by OR operator, which is disjunction operator, or you can say that OR logic gate. To construct circuit for this expression, first we need P and Q, not P and Q, P and not Q, and then we shall connect them all together. So first we have written P here, Q here, now, and then we draw lines, this and this. So this logic gate basically AND represents P and Q. So here we can write P, Q. As in the previous slides, we see that P and Q is abbreviated as PQ. Next, this logic gate basically AND represents the second expression, not P and Q. So here we have not P. So P, we draw a line from here to here, and then we draw a not operator, and then this goes to AND. What does it mean? Here we have not P, sorry. Here we have not P, and we draw another line here which represents Q. Here we have Q. Here we have not P, and here we have Q, and we construct here in an AND operator which gives us output not P and Q. This here in this here we have P and Q, the first expression, this one. At the last we need P. We draw a line here which comes as the input of AND, and we have not Q, and we draw a line here for Q, and here we have drawn a not operator here Therefore we have here not Q, or not capital Q, as we have written here capital Q. Now the input here is P and input here is not Q, and we apply a not AND operator here, whose output is P and not Q, which represents these third bracket or third expression. Now all these expressions, these three expressions, this and this, they are connected by OR operator. So we draw a line from here to here, from here to here, and from here to here, and we constructed an OR operator here, whose input is what is the input of this OR operator. There are three inputs of this OR operator. One input is this, second input is this, third is this. So one input is this expression, basically the second input is this expression, and third input is this expression. And output is, what is output? Output is S, which is this expression. So we can construct complex circuits like this, which correspond to these Boolean expressions or logical expressions. So now how to find an input, how to find an output for a given input, we have discussed as in previous example. If P is a particular value of 1 and Q is 0, these are the inputs of this circuit. The outputs we have found in this example as 1. Similarly, if we give inputs here in this circuit, for example P is 1 and Q is 1, then we can find the output. Here we have 1 because we have AND operator, the input is 1 and 1, so the output is 1. Here we have 1 1, but here we have NOT operator, the input will come here 0, here 1, so the output will be 0. Similarly, output is 0, and we have OR operator with 3 inputs 1 0 0. As there is a OR operator, therefore the output will be 1. So we can find output if we are given the input of any circuit. Next, we shall see another example, a simple example here, following the circuit output of the following statement: x plus y and not y. So how to construct this is basically logically equivalent to x or y and not y, basically this. So we have two brackets here. We write xy. There are two propositions, this and this. So there is a OR between x and y. We constructed OR operator, and then not y. We need not y. We made a link from y to here. We draw a not operator, and then these two brackets are connected by AND operator, and we have drawn here an AND operator basically. So the output is S, which is given to this. So these are, I think these are sufficient examples to understand how to construct a circuit for a given logical expression, or sometimes called Boolean expression. And we have also seen here, if we are given the input of these propositions x and y, if we are given the inputs, we can find the output also corresponding to the given circuit. Yes. Any circuit. The examples, very simple examples of the circuits you see in the daily life in your homes, which is switches in series and switches in parallel. Switches in series means if you have two switches as you can see here in this circuit, P and Q, these are two switches, and there is a light bulb here, okay, and there is a battery here. If the switches are in series, means they are in same line, in series, when P is open and Q is open, the bulb cannot be lighted. So if P is closed, Q is open, bulb will be off. If P is closed, Q is closed, these two are switches, simple switches in a home, in a room. So if P and Q are both closed here, they are on, then bulb is on. If one of P and or Q is open, then the bulb we cannot make it on. So this is an example of circuit, of series circuit. If you have two switches and one bulb in a room, then until you turn on both switches, or here you can say close both switches, you cannot turn on the bulb. So this is basically corresponding to a AND operator, or you can say that AND logic gate. So its truth table can be expressed as, if we have P, Q, two switches, if P is closed and Q is closed, then the bulb will be on. If this is closed, we can see here the form of switch is open like this, and the form of switch is closed like this. Then the current passes through this wire and the bulb turns on. If switch is open, then the current cannot pass through this point, then and the bulb cannot be turned on. So if P and Q are two switches, we have these four possibilities. P is closed, Q is closed. If this switch is closed and this switch is closed, then bulb will be turned on. And if P is closed, Q is open, then bulb cannot be turned on. It will be off, it will remain off. If P is open, Q is closed, it will remain off. If both are open, it will remain off. So this situation, if we have two buttons or switches for a one bulb, then it has a circuit which is called switches in series, and in digital logic it is basically the AND, P and Q. Basically it's AND logic gate. Its truth table in the logical form, we can write PQ, P and Q, true, 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 false, 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 true, false, 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 false. Similarly, switches in parallel, if we have, for example, in the home, usually in kitchen or washrooms, people make two switches, one inside and one outside. So this is an example of switches in parallel. If you have two switches here, P and Q, P and Q, so this is an example of OR logic gate. Usually it happens, as I have told, in kitchens. When you enter the kitchen, there is a button outside the kitchen, and to turn on the button, to turn on the bulb, and there is a button also for the bulb inside the kitchen, so that you can turn on the bulb from inside and outside the kitchen. So this is an example of switches in parallel. So in this situation, if P is closed and Q is closed, if the switch P is closed, Q is closed, the bulb is always on. And if P is closed but Q is open, then the bulb remains on. If P is open, Q is closed, then also the bulb remains on. If both switches are open, means off, then the bulb is off. So this is an example of disjunction operator or OR logic gate, P or Q. So we can apply here a OR logic gate. In logical form, we can write the truth table like this as in terms of T or F and P, or in terms of logic disjunction operator. So these are the examples of daily life examples of disjunction and conjunction operators which you see in your homes or daily life routines. So next is how to design a circuit for a given input or output. So here, if we have a truth table, for example, in which we have 3 PQR. In this truth table, we have 3 propositions PQR, and the possibilities here in the truth table will be 8, as if we have 2 propositions PQ, there are 2 propositions, then its power 2 is 2 power 2. This is basically the number of propositions. We have 2 propositions, so we take 2 power 2, we have 4. If we have 2 propositions, we have 4 possibilities in the truth table, as we have seen in the previous truth table here. Here we have 2 PQ, 2 propositions, so the possibilities in the truth table will be 2 power 2, which is 4. This 2 represents basically the number of propositions. Now if we have 3 propositions PQR, then the 2 power 3 basically represents the number of propositions. 2 power 3 will be 8, so we will have 8 possibilities in the truth table. And how we write the truth table, for example, in this example, we have 2 power 2 4. So P, to write a truth table, we write P and we write 2 times true, 2 times false, and then 1 time true, 1 time false, 1 time true, 1 time false. We write the truth table in this manner, which is an easy way to write the truth table. The same procedure here for the 8 possibilities here. How we write the truth table? First we write 4 times true for P and 4 times 0 for P, and then 2 times for Q, which comes here true, 2 times false, 2 times true, 2 times false, and then for the last proposition we write true, false, true, false, true, false, true, false, and so on. We write truth tables in this manner. So if we have 3 propositions PQR, so what will be the output? So there are 8 possibilities of inputs for PQR. If PQR are all 1, then the output is what? 0 here. For a given, so we are designing a circuit for a given input output. If we have 3 propositions here and we are given this output, actually this S doesn't represent any logical expression, so this is simply an output which is given, and we have to construct a circuit corresponding to this output. So first of all, we shall locate the ones in the output. There are only 2 ones in this output. Ones means true. There are only 2 true outputs in this column, in this output. So we always construct circuit for the true values in an output. in the truth table. I repeat, to construct a circuit for a given input output, we are given this input, we are given this output. No matter what and where this output comes from, we see only the true outputs, which are these two columns, these two rows. In these two rows we have true 1, 1. We always construct circuits for only true values in the output. So first we locate the true values here. This is the same truth table, and then we locate also the inputs corresponding to this output. The inputs corresponding to this true output are these, this and this. Now we see that here, what is the input? Input here is 1, means 1 corresponds for P. Here we have also 1 or true, and here we have 0. 1 means Q and 0 means not R. So we write it as P and Q and not R, which represents 1, 1, 0 as input. The second, here we have 0, here we have 1, here we have 1. How we connect them? For 0 we write not P, and how we connect them? Using conjunction operator, not P and Q and R. This basically corresponds to input 0, 1, 1, and we have output this 1. Now, how to write the expression, the logical expression for these two outputs? Inputs are this is an input and this is an input, and we have two true outputs, 1, 1. How we write the logical expression for these outputs 1, 1? We write input P and Q and not R, the first input, and the second input is not P and Q and R, and we connect them using disjunction operator. So this is basically the logical form corresponding to the given input and outputs in the given truth table. So this is basically the logical expression. Now we have written a logical expression. How we write the logical expression? We see the input, we connect the input using conjunction operators, and we connect the outputs here 1, 1, which are true outputs, using disjunction operator. So this is how we write the logical expression by watching the inputs and outputs. Now we have to construct the circuit for this logical expression. So what is this? This is the circuit. What was the logical expression? Basically it was P and Q and not R, or not P and Q and R. Now to construct this circuit, first of all we see that we have 3 inputs, three propositions, P, Q and R. So here we also see that in brackets we have P and Q and not R. So the preference is given to the not within the bracket, and then the preference is given to the bracket, in fact. So first we construct a logic gate for this expression, and then we construct a logic gate for this expression, and then we connect both logic gates with each other. So to construct a circle, we write P, Q, R. Basically P will go to the AND logic gate here, as we have P and Q. So Q is the input of this logic gate, and here we have not R. So we have written R and we have made a negation operator here, and after negation, this is basically output of this negation operator is, or not logic gate is not R, and the input for this AND logic gate is P, Q, not R. So the output of this logic gate will be P and Q and not R. So this will be the output of this logic gate, basically corresponding to the inputs P, Q and not R. Similarly, we construct now a logic gate for this bracket, this expression. In this expression we have not P and Q and R. So here we have P, we have made a not here, basically not operator. This will make not P here. So if we give the input here P, we shall get, or the output will be not P, and not P will be used as input of this AND operator. The input, another input is Q and R. So now we construct an AND operator. The output of this AND operator will be not P and Q and R, which express the second bracket here. Now in the logical expression, we see that these two expressions are connected by disjunction operator. So we connect these two by using a disjunction or operator. The output will come here, S. Now what is S? S is basically this logical expression. S is equivalent to basically P and Q and not R, or not P and Q and R. So this is basically the circuit which corresponds to the given inputs and output in this truth table. So if we are given a truth table, we can write the corresponding logical expression which represents the output. I repeat here, we consider only those outputs which are true, as we have considered only one here and one here, and the corresponding to these truth values, we choose only the inputs which are corresponding to the true values here of the output. By using these, we can write the logical expressions which represents this truth table, or which represents this output. Actually this output, the logical expression, this represents this whole output, and then corresponding to the logical expression, we can construct a circuit. We shall see how to reduce a circuit or prove two circuits to be equivalent. For example, if we take the same circuit as we have constructed in the previous example, P and Q or not P and Q, or P and not Q, we have found that the circuit corresponding to this expression, logical expression, is this. Now using laws of logic, we can simplify this logical expression, as we have, if we take left hand side P and Q and not P and Q and P and not Q. For today we stop here. The summary of today's lecture is, we have studied basic logic gates, circuits we have constructed circuits using basic logic gates, and for given inputs and outputs we have learned that how we construct or how we build circuits, and we have also studied equivalent circuits, how we can simplify a circuit into a simple circuit. We have also seen some applications of the logic in the Boolean algebra and half adders. We have studied half adders and full adders. Allah Hafiz.